Imagine a world where we can not only read the secrets encoded in our DNA, but also rewrite them with the same precision and creativity that we use to program computers. This is the promise of the DNA operating system, a groundbreaking concept at the intersection of biology, software, and hardware. At its core, this idea envisions a hybrid biodigital platform that allows us to interpret, modify, and reprogram genetic information in a controlled and highly sophisticated manner. Much like installing apps on your phone or writing code to direct a computer, a DNA operating system would empower us to write instructions for living cells, opening up extraordinary possibilities in medicine, synthetic biology, and beyond. Building such a system requires several major steps, each drawing from the latest advances in both biology and computer science. The first step is to design a platform for biological programming. This means learning the language of life, the genetic code, and mastering the tools that allow us to edit it. Technologies like CRISPR-Cas9, base editors, and prime editors have revolutionized our ability to make precise changes to DNA. Imagine developing a genetic compiler, a software tool that takes written genetic instructions and translates them into strands of DNA capable of producing insulin, fighting viruses, or even creating bioluminescent cells. This is the foundation for programming life itself. Next, we need a user interface, a control panel that lets scientists and engineers interact with the genetic programs they create. This is where the concept of a biological operating system, or BioOS, comes into play. By building sophisticated software that models the behavior of genes and cells, we can predict how a living organism will respond to genetic interventions. Artificial intelligence and deep learning models can simulate complex cellular reactions, helping us anticipate both the intended effects and potential side effects of our modifications. Current tools like Benchling, Ginkgo Bioworks, and Geneaios are already paving the way, allowing researchers to design and test genetic circuits with unprecedented ease. Once the genetic program is ready, it must be delivered to the living cells. This is achieved by synthesizing the programmed DNA, or by using viral vectors to transport the genetic code into target cells. Some researchers are even exploring bioelectronic interfaces, which could one day enable direct communication between digital devices and biological systems. Although these technologies are still in their infancy, they hint at a future where we can transmit instructions to cells just as easily as we send messages between computers. No system is complete without feedback, diagnostics, and error correction. In the DNA operating system, this means monitoring the effects of genetic changes using biosensors, RNA sequencing, and advanced machine learning algorithms. These tools provide real-time feedback, allowing us to diagnose problems and refine our genetic programs, ensuring safety and reliability as we reprogram life at the molecular level. This vision might sound like science fiction, but it's already being pursued by some of the world's leading innovators. Elon Musk's Neuralink is pioneering brain-machine interfaces with the potential to one day extend these technologies to cellular communication. Google DeepMind's AlphaFold has unlocked the ability to predict protein structures, laying the groundwork for precise biological engineering. Companies like Ginkgo Bioworks are rewriting genetic code as if it were software, while teams at MIT and Harvard are developing the foundations of a true biological operating system for synthetic organisms. If you're inspired to join this revolution, there is a clear path forward. Begin by studying molecular biology and genetics through platforms like Coursera or Khan Academy. Learn the techniques of gene editing with CRISPR and DNA synthesis using resources like Benchling and AdGene. Master programming languages such as Python and explore bioinformatics tools like BioPython. Finally, immerse yourself in system thinking and synthetic biology by engaging with communities like iGEM and exploring cutting-edge research. The creation of a DNA operating system marks a bold new chapter in the story of science and technology. It's not just about coding new life forms, it's about redefining what it means to program reality itself. This fusion of biology, artificial intelligence, and engineering represents the next frontier, where the line between the digital and the biological begins to blur, and humanity takes its first steps toward programming the very code of life.